Welcome in. Today we are settling in to look at something that honestly fundamentally shifts how you evaluate and really construct artificial intelligence systems.
It really does. It's a completely different lens.
Yeah, and if you're building an app right now, using an LLM API or even just heavily using these models in your daily workflow, you have probably hit a very specific wall.
Well, absolutely. Everyone hits it eventually.
Right. And we are pulling our source material today from Rooted Layers AI Insights grounded on research. We're going to refer to it naturally as the post throughout our conversation.
It's good.
And the post presents a premise that completely counters the prevailing narrative in the industry right now. Here is the hook. When an AI agent fails at a task,
Like getting stuck in a loop.
exactly, getting stuck in a recursive loop, or maybe it hallucinates an API call, or just completely bungles a multi-step data pipeline. When that happens, builders almost always blame the base model.
There's the default reflex.
It is. The reflex is to assume the model simply lacks the parameter count, or the inherent intelligence to complete the job.
And so they just wait for the next generation.
Right, they think, we'll just wait for GPT next or Claude next. But the Post argues this is usually the completely wrong culprit. The real problem isn't the model's baseline intelligence at all.
No, it's that the workflow lacks the appropriate reasoning scaffold.
Exactly. Even an incredibly capable frontier model will fail if the task requires decomposing a problem, or interacting with live tools, or searching for alternative paths.
If the system architecture hasn't been explicitly designed to facilitate that.
Yes. If the scaffold isn't there, the model falls over.
And that core observation really sets the analytical agenda for our discussion today. Because our goal here is not to just sit around and admire a theoretical taxonomy of AI capabilities.
Right, no textbook stuff.
Exactly. We are going to unpack the mental models and the actual architectural patterns behind how an agent should truly structure its internal problem solving before it ever executes work.
The actual mechanics.
Yes, we are approaching this from a strict engineering perspective. How do you select the absolute cheapest, lowest latency reasoning structure that reliably solves a specific task?
Because cost and latency are everything in production.
They are. I mean, in software engineering, you don't use a massive distributed microservices architecture for a simple static website, right?
No, of course not. That's overkill.
It introduces unnecessary latency, way more failure points. And the exact same applies to AI agents. If you over-engineer the reasoning scaffold, you waste massive amounts of compute and time.
But if you under-engineer it.
The agent hallucinates or crashes.
Right.
Finding that precise architectural balance, that is the actual work of building AI right now.
Okay, let's unpack this. Because to reach that optimal balance, the Post makes a critical distinction right out the gate. It separates reasoning from planning.
A hard line between the two.
Yes. It points out that reasoning is not just this one monolithic capability. You have lightweight default methods, you have reliability overlays for error correction, and then these highly expensive escalations that involve exploring multiple computational branches.
Which we'll get into.
We will. But fundamentally, the text draws a hard line between reasoning, which it defines as verbal problem solving that occurs entirely internally, never touching the external environment.
Just isolated.
Right, isolated. And planning, which is the active sequencing of operations in a dynamic, real-world state.
And it is a boundary you absolutely have to internalize to understand why agents succeed in the lab but just completely fail in production.
Why is that gap so wide?
Because we need to separate verbal problem solving from action taking. The context windows of these models, they're static. But the real world is entirely dynamic.
It's messy.
Very messy. An AI can sit in a vacuum, process its tokens, and generate a logically sound, highly optimized block of code, say, or a strategic proposal.
And that's reasoning.
That is reasoning. It synthesizes training data and previous tokens to output a localized solution. But that same model will often just crash when you ask it to take that exact reasoning and apply it against an environment that pushes back.
Give me an example of an environment pushing back.
Think about deploying that code to a server where the dependencies clash, or querying a database that returns an unexpected null value.
Right. The model didn't predict the null value.
Exactly. Handling that requires planning. It requires Executing an operation, reading the state change, evaluating the delta between the expected state and the actual state, and then dynamically sequencing a new set of operations based on reality.
A useful way to think about this is that we are moving away from treating LLMs as a bag of prompts.
A bag of prompts, yeah.
Where you just stuff instructions into the context window and parse whatever comes out. We're moving toward a structured engineering menu.
Modular pieces.
Right. To really illustrate the difference between reasoning and planning, consider an AI tasked with optimizing a complex mathematical proof.
A classic reasoning task.
Exactly. It processes the axioms, searches its internal latent space, and outputs the proof. It did that entirely internally. No external pushback.
Flawless execution.
But now, contrast that with asking an AI to manage a cloud infrastructure migration.
Oh, a nightmare.
Right. The AI might reason out a perfect sequential plan. It says, I will spin down server A, migrate the database to server B, and update the DNS.
Sounds great on paper.
It sounds perfect, but when it actually tries to execute, it finds out the database on server A is locked by an active background process.
And boom.
Boom. The static reasoning trace is instantly invalidated. The environment pushed back.
The static plan is dead.
The system has to pivot. It has to read the lock status and sequence a totally new set of API calls based on this live state. That is planning.
And the post emphasizes that these two domains require entirely different architectural scaffolds.
You can't use the same tools.
No, you really can't. A pure reasoning method, like a heavy chain of thought prompt, that might drastically improve the quality of a synthesized report, where all the data is already provided in the prompt.
Sure.
But if you try to solve a planning problem using only a reasoning scaffold, like if you just tell the model to think step by step in a vacuum, it is going to fail.
Because it can't see the database lock.
Exactly. It will output a highly articulate, very convincing sequence of how it would execute the migration, but it has absolutely no mechanism to actually observe the database lock or handle the API errors that follow.
It's just confidently narrating a fantasy.
That's exactly what it is.
So if reasoning is this internal token generation process, and planning is the dynamic interaction with an external state, what bridges the gap?
The control loop.
Right. How do we connect the internal logic to the external execution? That leads us to the control loop pattern that the post considers the absolute default foundation for any agentic system.
The baseline.
The baseline. Stage 1 is decomposition, and stage 2 is the react loop. Let's look at decomposition first. Okay, this is the practice of taking a massive, high-entropy task and strictly bounding it into a set of sub-goals. The post points to frameworks like least to most prompting and take a step back.
Instead of one giant prompt.
Exactly. Instead of passing a massive prompt and expecting a final output, you are forcing the model to generate intermediate artifacts.
And decomposition is vital because builders frequently mistake an AI's failure on a complex task as a lack of fundamental intelligence.
When it's actually...
When in reality, it is a context management failure. Think about it. Human engineers don't sit down and write a full-stack application in one unbroken stream of characters from the front end to the database schema.
No one does that.
Right. We write pseudocode, we define the interfaces, we build the schema, and then we write the functions. The post highlights that defining these intermediate artifacts prevents the model from having to calculate an incredibly complex multi-branching probability distribution all at once.
It narrows the focus.
Exactly. By forcing it to say, first, output the JSON schema for the database.
Stop.
Right. Now, using only that schema, write the database connection utility. Stop. You drastically reduce the token prediction load at any given node in the process.
It is the exact equivalent of writing the pseudocode before compiling the actual program.
Spot on.
And the take a step back paper mentioned in the post is really relevant here. It posits that failures are often conceptual rather than mechanical.
What do you mean by that?
Well, sometimes a model fails at a physics calculation, not because it can't do the math, but because it jumped straight into the math without defining the underlying physical principles first.
Ah, it lost the context.
Exactly. Prompting the model to literally take a step back and define the abstract principles first creates a grounded context for the subsequent calculation.
That makes total sense.
But once the task is decomposed into these sub-goals, we move to stage 2, the react loop.
Which stands for synergizing reasoning and acting.
Right.
And React is the operational backbone for any tool using agent. It enforces a rigid, cyclical progression.
Thought, action, observation.
Thought, then action, then observation. And why is this specific loop so critical to the practical stack? Because it is the mechanism that actually joins the reasoning to the planning.
It's the bridge.
It's the bridge. It forces the model to ground its next token prediction in the current observable state of the world, rather than relying on its static training weights or its own previous assumptions.
And this fits a broader pattern we're seeing across the entire field of agentic architecture. We are transitioning from single-shot, zero-context inference toward continuous loops of interaction with live environments.
Whether that is executing Python in a sandbox, parsing a live DOM in a web browser, or querying a SQL database.
Let's trace a React loop in a realistic engineering scenario, just to ground it. Suppose you have an automated DevOps agent and a monitoring alert fires, high latency on the payment gateway.
Okay, classic incident response.
Right. Now, a standard model without a loop might just spit out a generic troubleshooting guide based on its training data. Have you checked the router? Completely useless in production. But an agent running a React loop operates deterministically. First, the thought. It thinks, the payment gateway is experiencing latency. I need to check the current CPU load and active connection count on the payment microservice.
It forms a hypothesis.
Yes. Then, the action. It outputs a specific shell command or API call to the monitoring tool to actually get that data.
It touches the world.
It touches the world. Then, the observation. The external tool executes the command and feeds the raw output back into the model's context.
So it sees the result.
Exactly. Observation. CPU load is at 98%, active connections have spiked to 400%, and then the loop cycles back to a new thought based on that reality.
So the new thought is,
The service is under a traffic spike or a DDoS attack. I need to query the recent traffic origins.
the crucial distinction in that sequence is that the React loop tests hypotheses against reality. It doesn't assume the cause of the latency, it queries the state.
It checks its work.
Exactly. If the initial shell command returned an authentication error instead of the CPU load,
Which happens all the time.
all the time,
Yeah.
the next thought in the loop would just be, the query failed due to invalid credentials. I need to retrieve the updated API key from the secret manager and retry.
It adapts to the friction.
It adapts.
Yep.
The post argues that React must be your default architectural pattern whenever external state is involved. Without it, the model is essentially hallucinating a perfect world where its commands never fail and data never changes.
Which we know is never true. But relying on a React loop assumes that the model's intermediate thoughts and actions are generally correct.
Right.
What happens when that interaction fails, not because the environment pushed back, but because the model's internal reasoning on that specific step was just weak? Or what if it hallucinates a parameter in the API call?
Then the loop breaks down.
Exactly. We need mechanisms to catch and correct those localized failures before they corrupt the entire sequence. And that brings us to the reliability overlays.
The safety nets.
The safety nets. The post details several methods to reinforce weak first-pass reasoning. We've got self-refine, reflection, and chain of verification, which is known as COOV.
Let's break down the mechanics of these overlays because they apply to very different failure modes.
We will start with self-refine.
Self-refine is a localized graph critique revise loop. The model generates an output, and then you programmatically prompt it, often using a separate system prompt or even a completely different, smaller model to critique that specific output.
So it grades its own homework.
Basically, it identifies logical gaps or formatting errors and generates a revised version. And from a cost perspective, the post notes this is relatively inexpensive.
When do you use it?
You deploy self-refine when the initial output is structurally close but perhaps lacks clarity, or when a localized block of code has a minor syntax error.
So it's not a total rewrite?
No. It relies on the premise that it is computationally easier for an LLM to verify and critique a given output than it is to generate a flawless output from scratch.
It is essentially an automated code review step, just a quick polish.
Exactly.
But then the post introduces reflection, which it categorizes as verbal reinforcement learning. If self-refine is a local code review, what is the architectural shift with reflection?
The shift is entirely in the temporal scope and state persistence.
Okay, unpack that.
Self-refine is entirely stateless across sessions. It only cares about fixing the immediate output in the current context window. Once the session ends, it forgets everything.
Right.
Reflection persists the critique across multiple independent attempts at a task by writing to an external episodic memory.
It remembers.
It remembers. Instead of just rewriting a failed block of code, an agent using reflection analyzes the stack trace of the failure, synthesizes a natural language lesson about why it failed, and actually stores that lesson.
To give a concrete example, if the agent writes a Python script that fails because it tried to use a deprecated method from an older version of a library.
Very common.
Yeah. Reflection allows it to analyze the error, generate a lesson like, do not use method X in library Y, use method Z instead. And then it appends that to its memory store.
And that's the key.
Because the next time it approaches a similar task, it pulls that lesson into its context window before it generates the first draft.
Precisely. The post advises deploying reflection in environments that provide deterministic, binary feedback.
Like a pass-fail.
Yes, like compiling code, where it either passes the test suite or throws an error. It requires an environment where repeated iteration is acceptable and where the failure signals are clear enough for the model to synthesize a valid rule.
So that distinction is clear. Self-refine handles immediate execution errors in the moment. Reflection handles persistent conceptual errors over time.
Exactly.
But then we arrive at the third overlay, and here's where it gets really interesting. Chain of verification, or COVE.
This is a big one.
It is. The post highlights COVE as the most critical pattern for factual safety. It represents a fundamental departure from how most builders handle truthfulness right now.
Because the standard way is broken.
Completely broken. Instead of asking the model to review its own reasoning trace holistically, COVE decomposes the verification into an entirely isolated, independent step.
We really have to look at the token-level mechanics here to understand why COVE is so necessary.
Yeah, let's get into the weeds.
A very common anti-pattern in the industry is to generate a massive synthesis of data and then append a prompt at the end saying, "Are you sure this is correct? Double-check your facts."
I see that everywhere.
It's everywhere. And the post strongly warns against relying on self-consistency within a single context window for high-stakes factual work.
Why doesn't it work?
Because LLMs are autoregressive, meaning they predict the next token based on the sequence of preceding tokens. The previous tokens exert a massive gravitational pull on the output.
They anchor the model.
Heavily. If a model has just spent 800 tokens confidently articulating a hallucinated metric or a fabricated legal precedent.
Which they love to do.
They do. The statistical weight of those 800 tokens makes it highly probable that the model will simply validate its own hallucination when you ask it to double-check.
It is statistically compelled to agree with its own prior output just to maintain sequence probability.
Exactly. It can't escape its own gravity.
So how does COVE break that autoregressive gravity?
By strictly isolating the context windows. COVE forces the system to first read the original output and generate a discrete list of factual claims made in that text.
Just extracting the claim.
Just the claims. Then, and this is the critical architectural step it takes, each of those claims and poses them as independent verification questions to a completely fresh instance of the model.
A blank slate.
A totally blank slate, completely scrubbed of the original, potentially hallucinated draft. It operates as an independent, stateless auditor.
Let's apply this to a high-stakes scenario.
Yeah.
Imagine an AI agent tasked with parsing hundreds of pages of financial disclosures to identify potential liabilities for a merger.
High stakes.
Very high stakes. If the agent hallucinates that a specific subsidiary is debt-free when it actually carries a massive liability, the downstream consequences are catastrophic. Millions of dollars.
Right. And if you just ask the model to review its own summary.
It will likely skim its previous tokens and reaffirm the hallucination. Looks good to me.
Exactly. But with COVE, the system extracts the claim. The claim is, the draft states subsidiary X is debt-free.
Okay.
It then spins up a fresh context window. It passes only the raw financial documents and the specific question, what is the debt status of subsidiary X?
No mention of the previous draft.
None. The isolated model queries the documents, finds the liability, and returns the raw fact. COVE then programmatically compares this isolated fact against the original draft and forces a localized revision.
That is so powerful. It is not a superficial grammar polish. It is a rigorous, cryptographically separated fact-checking architecture.
And that is exactly why the post dictates that COVE is non-negotiable for high-stakes data synthesis.
Oh.
Medical summaries, financial reports, or any pipeline that triggers an irreversible downstream action.
Verification must be mechanically separated from generation.
Non-negotiable.
Okay, so these reliability overlays self-refine, reflection, and COVE. They are highly effective for localized errors and factual grounding.
Yes.
But they assume the core reasoning path is generally sound. What if the task is computationally brittle?
That's a different beast.
Right. What if the model executes a 10-step logic puzzle, gets it right 20% of the time, but completely cascades into failure the other 80% of the time due to minor token prediction variances early in the prompt.
One wrong step and the whole thing collapses.
Exactly. Or what if the task features massive state space complexity, where every single decision opens up multiple viable paths, like a complex scheduling algorithm or advanced logistics routing?
The baseline architecture just fails there.
It totally fails. And we must move to section 4, the expensive escalations.
The heavy artillery.
Heavy artillery. The post outlines heavy-duty search methods here: self-consistency tree of thoughts, or TOTU, LATS, which is language agent tree search, and a highly specific method called LLM plus P.
Let's analyze self-consistency first, as it tackles that specific issue of computational brittleness you mentioned.
Okay.
Self-consistency tackles brittleness through parallel sampling and majority voting. As we noted, a single reasoning trace is highly vulnerable to minor variances.
Right.
If the model makes one slight logical misstep on step 2 of a 10-step mathematical proof, the entire downstream output is corrupted.
It's ruined.
Rather than trying to build a complex overlay to catch that specific error, self-consistency attacks the problem statistically.
How does it do that?
You run the exact same prompt at a higher temperature setting, meaning you introduce more randomness into the token generation across 5, 10, or 20 parallel instances simultaneously.
Wow, 20 instances.
Yeah, you generate multiple diverse reasoning paths, parse the final answers from each of them, and then you just select the answer that appears most frequently.
The consensus.
The consensus.
If you are building a deterministic system, it is the exact equivalent of running a redundant consensus protocol. If 8 out of 10 parallel traces land on the same numerical output via entirely different reasoning paths,
You can trust it.
the statistical confidence in that output is exceptionally high, even if you didn't manually parse the intermediate steps yourself.
Yes, and the post notes, this is incredibly effective for logic-heavy deterministic tasks where there is a definitive correct answer, but the path to get there is just very brittle.
But there's a catch.
A massive operational trade-off. You are linearly scaling your compute cost and your latency by the number of samples.
Right.
If you run 15 parallel traces, your API cost is 15 times higher.
Ouch.
And your time to first byte is gated by the slowest trace of the 15. Therefore, you only deploy self-consistency in environments where accuracy strictly overrides latency and cost constraints.
Like background data processing.
Exactly. Not real-time user-facing applications. You'd never use this for a chatbot.
Right, the user would be waiting forever. And then we reach the absolute heaviest artillery tree of thoughts and LATs.
The big ones.
These methodologies abandon the linear progression of standard prompting entirely. They transform the reasoning process into a formal state space search. And the post is highly explicit here. These are extreme escalations, not standard architectural starting points.
This is a very common trap for engineering teams reading the latest RxFIF papers. They want to implement the coolest new thing.
Yes.
But Tree of Thoughts allows an AI to systematically explore multiple reasoning branches simultaneously. It generates multiple possible next steps or thoughts, evaluates the viability of each using a programmatic value function, and decides whether to pursue a branch, abandon it as a dead end, or backtrack to a previous node.
Like solving a maze.
Exactly like solving a maze. And LATS, or Language Agent Tree Search, pushes this even further. It merges the branching architecture of Tree of Thoughts with the environmental grounding of React.
Oh, combining them.
And it applies a Monte Carlo tree search algorithm to navigate the state space. It uses the actual environmental feedback, like whether an API call succeeded or failed, as the value function to score the nodes and guide the search.
It is computationally very similar to how a chess engine evaluates board states.
That's a great analogy.
It projects multiple moves ahead, evaluates the board, and prunes the branches that lead to a disadvantage. If your agent is trying to optimize a complex logistics routing problem with live traffic data and strict delivery windows, LATS is incredibly powerful.
Unmatched.
It can test a route, hit a lock state, back up, and optimize an entirely different path. But the orchestration overhead is just staggering. You have to maintain the tree state, manage the context window for every single node, and handle the backtracking logic.
The latency is immense. And this brings up the LLM plus P methodology the post mentions.
Yeah, let's talk about LLM plus P.
LLM plus P recognizes that LLMs fundamentally are actually quite poor at deep optimal planning in highly constrained environments.
They aren't calculators.
They aren't. So instead of forcing the LLM to search the tree itself, LLM plus P uses the LLM simply as a translation layer.
How does that work?
The LLM takes the natural language problem, translates it into PDDL, which is Planning Domain Definition Language, a classical symbolic planning format.
Old school AI.
Very old school. It hands that PDDL to a deterministic classical solver like fast downward to compute the mathematically optimal plan, and then the LLM translates the result back into natural language.
That is a brilliant architectural separation of concerns. You use the LLM for its semantic understanding the thing it's actually good at,
Right.
but you offload the complex state space search to a traditional algorithm built specifically for that purpose.
Exactly. Play to their strengths.
But whether you use LATS or LLM plus P, the core trade-off paradigm remains exactly the same. The author explicitly warns against defaulting to state space search. If your task is essentially a straight deterministic pipeline, if simple decomposition can map the route, adding a Monte Carlo tree search is an unjustifiable waste of compute.
It's burning money.
Burning money. Your job as a system architect is not to implement the most complex paper you just read on Arcure.
No, it's not.
It is to deploy the most efficient architecture that meets the reliability threshold.
Which transitions us perfectly into the operational synthesis.
Right.
We've analyzed all the primitives,
Yeah.
decomposition, and React.
The baseline.
We have explored the error correction overlays,
Yeah.
self-refine, reflection, and cove.
The safety nets.
And we have outlined the expensive escalations, self-consistency, and tree search. How do you actually integrate these into a coherent system? The post provides a definitive 5-step build order. This is the master blueprint.
Let's walk through that build order and apply it to a realistic production scenario just so the scale and complexity is crystal clear. Let's assume you are building an agentic system to handle automated customer refund processing across multiple internal databases.
Very standard enterprise use case.
Right. Step 1. You start with decomposition and React. This is the baseline. You break the refund process into bounded steps. Verify user identity, check transaction history, validate refund policy. You use the React loop to query the CRM and the payment gateway, ensuring every single decision is grounded in live state.
And honestly, for a vast majority of standard refunds, this architecture alone will successfully resolve the ticket.
Most tickets are simple.
Yeah.
Exactly. Step 2. You introduce the verification step. Before the agent executes the irreversible action, which in this case is triggering the actual API call to transfer the funds.
You don't want to mess that up.
No, you don't. It runs a localized self-check to ensure the transaction ID and the refund amount match the policy output exactly.
Okay, so that's step 2. Step 3. Introduce self-refinement, but restrict it to near-miss scenarios. If the agent generates the correct refund authorization, but formats the internal logging JSON incorrectly.
Which happens all the time with LLMs.
Constantly. You use a cheap self-refine loop to fix the syntax before it hits the database.
So the core engine is operating, you decompose, you interact via React, you verify the critical action, and you refine the syntax. But what if the edge cases require more reliability?
That's step 4.
Step 4, you add self-consistency, but strictly gated by accuracy demands and latency budgets.
So not for everything. Definitely not. If it is a complex, high-value enterprise refund where the policy is deeply ambiguous and is running as an asynchronous background job where the user isn't waiting on a live chat.
Like a batch process overnight.
Exactly. Then you might run 3 parallel traces to ensure the policy interpretation is consistent before proceeding.
And finally, step 5. You escalate to search methods like Tree of Thoughts or LAT only for high-value, branching-heavy tasks where all simpler scaffolds have failed.
The absolute last resort.
Right. If the refund requires navigating a cascading series of microservice rollbacks where each step depends on the success of the previous, and failures require complex alternative routing only, then do you incur the overhead of a formal tree search?
It is a strict decision matrix. If the task is multi-step but deterministic, rely on decomposition.
Keep it simple.
If it touches live state, you must use React. If factual accuracy is paramount, implement Cove. If the task requires exploring genuine alternative paths, escalate to search.
So what does this all mean when these systems fail in production? The post lists several critical anti-patterns, and this is where the theoretical meets the practical.
Or the rubber meets the road.
Exactly. Builders often overuse chain of thought without environmental grounding, essentially letting the model hallucinate a perfect execution path without ever querying the live state.
A huge mistake.
Or they allow the model to plan actions for which it lacks the requisite API tools, resulting in terminal errors.
But the most profound insight in the entire text, and this is the trap that almost every team falls into at some point, is the warning against confusing verbal fluency with validated reasoning.
Yes.
This is a massive psychological vulnerability for humans evaluating AI.
Let's drill into that, because large language models are, by definition, optimized for linguistic fluency.
They are built to sound good.
They can output a multi-paragraph architectural proposal that is grammatically flawless, confidently structured, and uses all the correct industry terminology.
And as humans, we rely on a heuristic that equates eloquent, structured communication with underlying intelligence and factual accuracy.
If it sounds smart, it must be smart.
Exactly. The models have effectively weaponized that human heuristic. An AI can eloquently articulate a completely flawed sequence of actions. It can generate a highly convincing chain of thought that hinges on a hallucinated API endpoint or a fundamentally incorrect assumption about the database schema.
And if an engineer evaluates the agent's performance by simply reading the reasoning trace and thinking, wow, this looks incredibly sophisticated, the plan is logically laid out.
They have fallen for the fluency trap.
Hook, line, and sinker.
They are evaluating the quality of the prose, not the validity of the state changes.
Which fundamentally changes how we must evaluate these systems entirely. You cannot judge an agentic stack by the apparent sophistication of its internal monologue.
You just can't.
The post dictates strict, objective evaluation metrics. You evaluate based on post-verification success rate. Not how often the model generated a plausible-sounding plan, but how often the final verified execution actually resolved the ticket or compiled the code.
Real-world results.
Exactly. You evaluate based on tool-grounded plan coherence. Does the generated sequence of actions actually map to the specific API constraints of the environment? And crucially, you evaluate based on latency and token cost per solved task.
The cost per solved task metric is the ultimate reality check.
It really is.
If you architect a LATS-based agent that resolves an edge case support ticket perfectly, but it consumes 3 minutes of compute time and costs $1 in API calls per execution,
You're going to go bankrupt.
you have built a failed system for a high-volume enterprise environment, regardless of how elegant the Monte Carlo tree search was. The central thesis of the author is this: the objective is not to deploy the most advanced, complex reasoning methodology available. The objective is to deploy the absolute lightest, most cost-effective reasoning structure that pushes the task over the reliability threshold.
It is a pure engineering discipline. We have covered an immense architectural landscape today.
We really have.
We have transitioned from the rudimentary view of AI as a magic prompt box to a sophisticated understanding of it as an integrated system requiring deliberate, staged architectural design. We established the critical boundary between static internal reasoning and dynamic external planning.
Crucial distinction.
We laid down the foundational baseline of decomposition to handle context limits and React loops to ensure environmental grounding. We explored the rigorous mechanics of the reliability overlays, self-refine for immediate syntax correction, reflection for persistent episodic learning, and for cryptographically isolated factual auditing.
And we examined the extreme escalations of self-consistency in formal state-space search, contextualizing them strictly as high-cost tools of last resort.
If there's a singular takeaway from this framework, it is that true expertise in AI system design is defined by restraint.
Restraint is everything. It is incredibly tempting for builders to reach for the most complex, cutting-edge search methodology they just read about. But the mark of a mature architect is knowing precisely when a simple decomposition and a basic React loop will solve the problem elegantly and cheaply.
And possessing the operational discipline to stop there.
Exactly. Stop there.
Restraint as the defining metric of expertise. As we conclude this deep dive into the insights from rooted layers, I won't leave you with a final thought to mull over, building directly on that psychological trap we discussed regarding evaluation. The post warned us not to confuse verbal fluency with validated reasoning. Think about your own interactions with these models, whether you are building with them or just using them in your daily work.
It's day to day.
Yeah. The next time you prompt an AI, and it returns a beautifully written, highly structured, incredibly confident explanation of exactly how it is going to solve a complex problem for you, I want you to pause. Ask yourself, are you being swayed by the sheer linguistic fluency of its output? Or does the underlying system architecture actually possess the grounded, interactive, error-correcting reasoning scaffold required to execute that plan in a dynamic, unpredictable environment?
That's the real test.
Is the model just generating highly probable text, or is it truly equipped to act? Thank you for joining us on this deep dive.